Assalamu alaikum, dear students. We're back with another video lesson. After covering chapter 5, now we're in chapter 6, or you can call them unit 6. And in chapter 5, we said that we use electricity to create magnetism here. And of course, we said in chapter 6, we're kind of like doing the reverse, especially for 6.1, let's say. And what we did is basically using magnetism to induce or to create or to generate, let's say, electricity. So this voltage that is induced, we call it electromotive force. And of course, we said, and of course, we're going to write it down this way, let's say. That is, of course, the symbol for the voltage that we're using here. That is the same as voltage, okay? Or you can say the potential difference as well. And that, of course, okay, I almost forgot what I was to say. And then this voltage that is induced, of course, let's say depends on various factors. We can, and by the way, Faraday, let's say, demonstrated this. And of course, we can say he was the one who found, for example, how to convert or how to use magnetism to induce electricity. What he used was this. Let's say bringing a magnet close to a coil of wire that was connected to a galvanometer. So once he, let's say, moved the magnet closer to a coil, he saw that the galvanometer shifted in one direction. Once he pulled the magnet out of the coil, let's say, the galvanometer needle shifted in the other direction, indicating that once you move a magnet closer to or out of the coil or far away from a coil, there will be an induced electromotive force. But he noticed that also when you hold the magnet still inside a coil, there will be no induced electromotive force. So he concluded that as long as there is a relative motion between the magnet and the coil, let's say, there will be an induced electromotive force there. Okay? But if there's no motion, there will be no induced electromotive force. And of course, this induced electromotive force will increase by, let's say inserting the magnet faster into the coil, or let's say pulling it out faster out of the coil, let's say, or of course if you increase the number of turns and other factors as well. And then after that, we talked about, let's say, the electromotive force induced from a conducting wire inside a magnetic field. We said the conducting, the magnitude of this conducting or the magnitude of this electromotive force that is induced will equal to B times L times V sine theta. And of course, it depends on, in another word, the induced electromotive force depends on the strength of the magnetic field, depends on the length of the wire that is only inside the magnetic field, and also depends on the velocity which you're moving the conducting wire within the magnet, and not forgetting this, the angle between the velocity, the direction of the motion, and the magnetic field strength as well, because that is also crucial, because that determines whether you want to have maximum, minimum, or somewhere in between the two, the amount regarding the amount of the induced electromotive force that is induced, you can say. And then, of course, we ended up, we covered this, by the way. So we said the induced electromotive force that is induced will be maximum. Remember this, if the magnetic field lines are, let's say, crossing or perpendicularly crossing, let's say, the cross-sectional area of the coil, just like this one, or you can see this one as well. Remember, this is the direction of the motion. That means these magnetic field lines are cutting through the cross-sectional area of the coil here. And we said that it will be less if it is tilted at some angle, you can see here, or this one here, that is the direction, let's say. You can see that this coil is cutting the magnetic field lines, but not perpendicularly, or you can say the magnetic field lines are not perpendicularly crossing the cross-sectional area of the coil here. And then we also talked about this one. If you move the coil, let's say this coil is, or the plane of the coil, you can see that it is moving, you can see, parallel to the direction of the magnetic field lines. In this case, there's no cuts between the two, so that means there's no electromotive force induced here. And of course, you can see as well, if you move, let's say, the coil this way, whether you're moving it forward, let's say, or backward, so it is, in either way, it is still parallel to this direction here. In that case, no magnetic field lines are cut. No magnetic field lines cut means no induced electromotive force in here. Okay, and then we ended up this question here, and I was saying, I hope you do answer the questions before I answer them. The first one says the process of creating a current in a circuit loop by changing the magnetic flux in the loop, what is it called? If you do remember, that is the definition of what? Of electromagnetic induction? Well, if you said yes, then well done, very good. So is it a self-induction? That is no. Is it a mutual inductance? No, we haven't reached that yet. Is it a magnetic induction? The answer is yes. What about the last one? It says electrical superconductivity. That is also a no. So the correct answer is electromagnetic induction. All right, what about this one here? This is also one of the very important questions here, and of course one of the recent past questions, you can say, yeah? Okay, you can say past was added question. All right, it says consider conducting wire pulled through a magnetic field B as shown in the corresponding figure. The polarity of the induced electromotive force of which of the following forms is correct? Now, so this is basically what we have, or what we went through the other lesson, yeah? So we said when you move a wire inside a magnetic field, remember it is not a closed circuit, it is just a conducting wire here. So we said one side will be positive, the other side will be negative. That is, you know, like as a base, let's say, for that. So as you can tell here, now I have, take a look, if you take a look at these two wires, these are both positive and these are both negative. So can we have a wire that is moved within the magnetic field, let's say, and can have both ends negative or both ends positive? No, so you can immediately cross out this one, because we said one side is going to be positive, the other side will be negative, depending on the magnetic field line and of course the direction of the movement as well, or the direction of the motion here. Now we're left with two conducting wires within a magnetic field. So which one is correct? Is it A or B? Now, in order to answer this properly, you'll have to use the right-hand rule. So how do we do that? Take a look. First of all, you do know that B, the direction of the magnetic field, is out of, you can say, out of the screen here. So for you, in this case, it's going to be out of the paper. Now that is 1 here, and you can see this is basically the direction of the motion, which is basically, you can say it is directly or to the right. So remember this, using the right-hand rule, you can say, set the direction of the motion, magnetic field, there's a force on a positive charge. So if I do this one here, you can see that this is the direction of the motion, this is the direction of the magnetic field, force, and of course this side here, or you can say this is the direction of the positive charges here, so positive charges at this end, negative charges at the other end. So this is going to be correct, but how about we check B as well, okay? Now, if you look at B here, the magnetic field line again are out of the page here, or you can say out of the screen here. The direction of the motion is still to the left in this case, yeah? Well, if I stand the other way, that is going to be to the right if we look at this one here. But still, as you can tell, so if that is the case, this is the direction of the motion. This is the magnetic field lines here. So the force on the positive charge is going to be downward, but you can see it's written negative over there. So that means that it's incorrect. Remember, negative is the back of your hand, which is, in this case, it has to be upward. So this is incorrect. And we already crossed out this one. So of course, the answer has to be option A. And I hope you got that one correct as well. Okay, now take a look at this one here. What does it say? The magnitude of the induced electromotive force in a straight conducting wire, let's say a straight conductor or a wire, depends on which of the following. So in order to do this, before even looking at the options, right, it is about conducting wire. It's at a magnetic field. So we said electromotive force, it is equal to B, L, V, and of course sine theta. So now, of course, based on this, you can judge whether an option is right or wrong. So the first one says the length of the wire in the field. So do we have this? Yes, so it depends on this. But what about the other options here? It says strength of the magnetic field. So that is also true. It depends on the strength of the magnetic field. And then C says the velocity with which the wire is moving through the magnetic field. That is also correct. So of course now we can say all answers are correct. All right, so that is how you tell whether it is right or wrong. Okay, now let's talk about something else regarding this. Perhaps this is not totally new because we've already covered some of these, but of course we'll be emphasizing, or we will talk about this in details. So how do we do this, or what is this exactly? That is basically the effect, or you can say change in the number of the magnetic field lines induces a current here. But remember, before current, first of all, there must be an induced electromotive force, there must be a voltage induced, then we can have the current. Why? Because current is basically the flow of the electrons through the circuit. So, and this electromotive force is like a force that drives, it's like a force that pushes the electrons through the circuit. Or if not, you can say electromotive force, that is the energy that is given to the electrons so that they can move within the circuit. So first of all, we must have an induced electromotive force, and that electromotive force will create a current through the circuit if the circuit is in a let's say closed, or if we have a closed loop, you can say, if we have a closed path, that is also true. Okay, so the first one says ways of inducing a current in a circuit here. So how do we induce, how do we create a current in a circuit? The first one, these are basically three of these ways are mentioned in the book, and of course this one here I've added to the table because only this three is, let's say, given in the table, but I've added this one as well, let's say extracting this from one of the questions as well, where we can change this one. We'll get to this one in a second. So the first one says, if a circuit, how do we induce an electromotive force, and then later on, of course, inducing a current in a circuit. The first one is if the circuit is moved into or out of a magnetic field. So if you don't remember, in the previous session we said it doesn't matter whether you move the magnet into the coil or the coil closer to the magnet. Whichever you're moving, as long as there is a relative motion between the two, then of course an induced electromotive force and then an induced current will be, or there will be an induced current as well. So here we have a coil here. You can say this is before inserting this one into a magnetic field. So moving this coil into a magnetic field, or you could say moving the magnetic field, let's say, onto the coil, that is also true. Whichever happens, there will be an induced electromotive force, and this induced electromotive force will create a current within the coil. Okay, that is the first one here. The second one, or the second method of generating, of inducing current, is this. A circuit is rotated in the magnetic field, you can say the angle, you can say, or the angle between the area of the circuit and the magnetic field changes here. So what we have here is, we're not moving this coil or this circuit into or out of the magnetic field. No, what we do is we're changing, we'll just rotate this coil within the magnetic field. But remember this, if you're rotating this coil inside a magnetic field, let's say let's say this pen is not a very good example, but let's just say this pen is the circuit here. The magnetic field line is basically outside. If that is the case, let's say, once you're doing this, let's say, imagine there's a coil. It's not, but still one part of a coil you can consider. So now at some point here, if you're doing this, let's say, maybe you can see that all these are crossing. Perhaps not a very good example for this, but we'll just I'll ignore this example because it's not, you can see it's not rectangle, so perhaps it doesn't help explaining this much. But here's what I want to remember this. This is basically, this is the orientation of the coil now. This is how you put the coil there. By doing this act, you can see that most of the magnetic field lines are passing through the cross-sectional area of the coil, or you can call it the circuit 2 here. So now what happens when you rotate the coil? Once you rotate the coil, it's almost like rotating it this way here. So you can see these magnetic field lines are now cutting the coil at some angle, and when the coil becomes totally, perhaps my hand will be a very good example. So that's good. Now zoom it in as well. So this, if that is the case, you can see all the magnetic field lines are, let's say, coming out of the palm of my hand here, creating or induced maximum electromotive force. Once you're doing this, now these magnetic field lines are cutting my, let's say, hand at some angle, which the induced electromotive force will be less. And then what happens when you keep rotating? You can see that these two would be parallel to one another. Now the magnetic field lines are outside, you can say, directly here, like this. And of course, let's say, or the coil, the orientation of the coil is also, you can say, into this direction as well. So these two will be parallel to one another. If it is parallel to one another, there's no cut, there's no electromotive force. And then after that, you do this, there is cutting, of course. After that, here now, there will be maximum cutting between the magnetic field lines and the coil. So we'll get maximum electromotive force in here. So by the way, so this would be what happens, that is before the rotation. Maximum magnetic field lines are cutting or passing through the cross-sectional area for this. And then you can see here now, you can say it is either less, or you can just say completely zero. No magnetic field line crossing the coil or the circuit. And if that is the case, no current will be induced. Okay, now that was the second method. So what was the first method? Moving a coil into a magnetic field, or moving the magnetic field, let's say, onto the coil. It doesn't matter. That was the first. Second, by rotating the coil inside or within the magnetic field. That, once again, that would alter or change the angle which the magnetic field line, let's say, is cutting through this. Imagine this. If this is the magnetic field line, this is the coil. If it is like this, you can see maximum magnetic field lines are cutting through the coil here. But once you rotate the coil, it becomes less and less when it is like this, that is parallel, no cutting at all, so 0, yeah? And then after that, of course, you tilt this one more, so it becomes like this and this until it becomes maximum again, and then this is how it continues. So that was the second method. The third method is, hopefully you can tell like what happens or what have happened here as well. You can see we have a lot of magnetic field lines here. All of these are pointing outward. Here I have fewer numbers there. You can see these are at least, let's say, 5 magnetic field lines, if not to scale, but this is just 1 magnetic field lines crossing this. So of course you're changing the strength of the magnetic field here, because we said one of the factors that determines the size of the electromotive force induced, it was B, it was L, it was V as well, of course, yeah, and sine the angle as well. Here we've reduced the magnetic field strength. Reducing this, of course, that also affects the electromotive force that is generated. So we can say by changing the intensity and or the direction of the magnetic field is varied. So these are both correct. So here you can see the intensity have changed. And of course the same thing is true if we reverse the direction of the magnetic field line here. So for example, the direction of the magnetic field lines is outward. I can reverse the direction and make it inward, let's say, into the board, let's say. And in that case, of course, I can have still induced electromotive force in this case. Okay, and then the fourth way where we can induce electromotive force is by this. The cross-sectional area has changed, or if we change the cross-sectional area of this. So as you can tell, previously we said here, let's say this is the angle, or we've changed this angle. You can see that a lot of magnetic field lines cutting through the cross-sectional area. But if I have a ring or any other shape, let's say, and if I, let's say this, considering this a wire, so I can stretch it, that means I can change the cross-sectional area from a circle into something like this. So when I do or make it this, so you can see here, the cross-sectional area of this one you can say here, or the cross-sectional area where the magnetic field lines are crossing, it is very little compared to what is there. So that means less magnetic field lines are cutting through the cross-sectional area of this. We're changing almost something from a circle to almost something very thin, just like, you can call it a wire or something very thin. There is less magnetic field lines cutting through this. As long as there is a change in the, let's say, magnetic field lines, the number of the magnetic field lines, the angle of the magnetic field lines cutting through this, or you can say the direction of the magnetic field lines, there will be an induced current here. But here's reduced, so the electromotive force that is induced will also be reduced in this case. So once again, remember, we have, or there are 4 ways where we can induce electromotive force. By moving a coil, a circuit, into or out of a magnetic field, or we can do, or we can move the magnetic field into or out of, let's say, across the coil, the circuit, or let's say away from the circuit. That is one. Second, by rotating a coil inside a magnetic field. Third, by increasing or decreasing, or even reversing the direction of the magnetic field lines, that will also induce electromotive force. And then, and of course, the fourth one was by changing the cross-sectional area of the coil. That will also change the number of magnetic field lines cutting through the coil, and of course changes the magnitude of the induced electromotive force. Now we have a question says, which of the following ways can induce a current inside a closed circular loop in here? By moving the circular loop into or out of the magnetic field? Isn't that the first option we've done, or the first step? We said we were talking about this. Yes, it was. So we can do that, right? So this one is true. Okay, but let's check out if there's any, or if there are any other options. It says by changing the magnetic field strength or its direction. That was the third step, yeah? Okay, or the third way, inducing electromotive force. It says or by, let's say, by rotating the loop inside a magnetic field. So these are also correct. So we can say all of them are correct. So by changing whichever of those that are mentioned will induce electromotive force, or you can say induce current as a result of that. That would also induce you can say induce current as well. So by whatever the x that we've shown will also affect the size of the induced current, or you can say it will induce the current, yeah? That would be for that. Now let's talk about the characteristic of the induced current here. So far, we've been saying that if you do this, there will be induced current, yeah? If you do that, there will be induced current, yeah? but how big of a current, or like what would be the size of the current that is induced? Or in a different way, let's say, what are the nature of the current that is induced here? So now in this, let's say from now on, we'll talk about it, let's say for the next few minutes, we'll be talking about the property of the current, or the properties of the current that is induced. Okay, so that'll be for that. All right, but before that, by the way, I've mentioned this before. Can we induce the current without inducing the electromotive force? No. So of course, first you must induce the electromotive force, the voltage. Then this voltage, of course, will induce the current within the circuit, you can say, if we have a closed circuit. So what happens exactly when a bar magnet is pushed into a coil of wire? So if you do remember, we've said it in the previous session, and of course we've repeated this time too in this session. We said when we, for example, when we bring a magnet closer to a coil, of course, let's say if it is connected to a galvanometer, you will see that the galvanometer shifts one direction. But once we pull the magnet out of the coil, the galvanometer shifts in the other direction. So that means when the magnet is pushed into the coil, the current that is induced will be in one direction, and then when the magnet is pulled away, then the current will be reversed. Yeah? In another word, it will be in the other direction here. So why or how does it happen? So let's talk about the nature of this current that is induced here. So we'll say, when a bar magnet is pushed into a coil of wire, the strength of the magnetic field within the coil increases. Isn't that interesting? So how or why does that happen? So consider this magnet is brought closer to this coil right here. So what exactly does it happen? The first thing is the strength of the magnetic field within the coil increases. So you can see here, all right, so consider, let's say okay, you have to consider this without a magnet. So how about if I just, let's say, cover this and redraw this so that you can see better. Okay, so what exactly will happen? So remember this. Now we have a magnet. This magnet is north and south, and of course we have a coil as well. Let's say this coil is connected to a galvanometer. Of course we could have just, okay, let's make it sharper here. Okay, so here's a galvanometer. Not this. Galvanometer. Okay, now here's a galvanometer, and of course this is the zero indicate. You can say 0. This side, let's say, is positive, the other side is negative. So what happens exactly when we bring a magnet closer to the coil here? First of all, we do have a magnetic field lines, you can say, around this magnet here. So these are the magnetic field lines around this. Perhaps these are not, you can say these are not perfect magnetic field lines, but of course you do understand this. So when we bring this magnet closer to the coil, when you bring this magnet closer to the coil, you can see that the magnetic field lines that are crossing the coil, or you can say over this coil, of course, increases, because now, let's say if we move this one away, you can see here, let's just see if we can do that too. Oh, no, this one here. Okay. All right, so obviously not. So imagine if we, for example, move this one away, you will see that there's no magnetic field lines lying on this coil here, so there's nothing there. But as you approach this magnet closer to this, of course, these magnetic field lines will be cutting, will be falling, let's say, across this coil. So they will cut through the lights, through the wires of the coil in this case. So as a result of this, we can say the magnetic field within the coil increases. That is the first thing that happens to the coil. And then what happens next? We can say a current is induced in the coil here, or in the circuit here. So once this happens, if you do remember previously, we said a current will be induced in the coil. So in another word, we can say this galvanometer needle would be shifting, let's say, to one side. Let's say it shifts us towards the positive direction here. That is what happens next. So we can say this induced current in turn produces its own magnetic field. Now that is, so basically this is chapter 6 here. Now what happens here is when there is a magnetic field, let's say, or you can say when there is a current induced in the circuit here, So this current that is induced in the circuit, it is the same as, remember, it is not what it is, but it's the same as if, watch this, it is the same as if I have, let's say, we said this connecting to this side, so let's make this one perhaps positive. So it is the same as if there is obviously current in the coil, yeah? If that is the case, it is the same as if, it's not true, all right, but it behaves like this, the same as if this coil is connected to a battery, let's say. And if that is the case, we said chapter 5, don't forget, current will flow through the circuit, but of course now this coil will have its own magnetic field lines. This coil will have its own magnetic field line. But this magnetic field line of the coil that is induced will be opposite to the one that is induced here. So we will say this magnetic field lines, and of course, are opposite to this one. So if this side is north, this side is also going to be north. And of course, these two are now opposing one another. But that is only when we bring the magnet closer to the coil. So this is what happens. What is next? The induced magnetic field line is opposite in direction of the increasing magnetic field. So this magnetic field line is still trying to come closer and closer and closer, but this one also trying to increase, like a growth in, let's say, strength, it becomes more and more. So the closer this one gets, the more this one becomes, so the more the opposition. Now these two will oppose one another, so this magnetic field line opposes the change, not this magnetic field line, the change in this magnetic field line. Because these magnetic field lines are trying to get closer, so there's a change in it, and this one tries to stop it from, let's say, getting closer or increasing further. The induced magnetic field, we said it is in opposite direction of that, then the direction of the two fields is opposite. The external field decreases. So we can say the external field now, these are, let's use this one also here, let's just add one more. So now these magnetic field lines are opposing one another, so of course now you can say the external field for this two will decrease as a result, because when you have two magnets opposing one another, it's almost like they cancel one another's magnetic field. If that is the case, we can say the external magnetic field lines as a result will be less, okay? So now, of course, I can erase this one. Hopefully you understood the idea here. So we can say that was the galvanometer. That is true when this is 0. Let me just go back to this. That is true when the magnet, or this magnet, is trying to approach this coil right here. So this is what happens. Let's summarize it real quick. When we bring this magnet closer to the coil, you can say the external magnetic field on this coil increases. That is the first case. Second, there will be an induced current in this circuit here. Now this current that is induced will produce its own magnetic field here. This magnetic field that is produced here will oppose the change in this magnetic field that is approaching. And of course these are in opposite direction. And of course as a result of this, the external magnetic field will oppose one another. Or you can say the external magnetic field will be less. If I do this one here, we'll say, of course, we have magnetic field lines here. Once these magnetic field lines are changing across this, there will be, you can say, a magnetic flux. The change in the magnetic flux, these are, by the way, for the external coil, you can say. So let me just write X for external. Okay, just for now, you could different symbol. So this change of this coil here, you can say, or this magnetic field, that'll be the number of magnetic field line falling, let's say, over the cross-sectional area of this. Now there will be an induced electromotive force here. We can say there will be an induced current in this one. Of course, first of all, there will be an induced electromotive force here. Okay, so this electromotive force, of course, would lead to an induced current here. And now this current will produce its own magnetic field here around this coil here. Now these two magnetic field lines, of course, you can say they will kind of like oppose one another. So as a result, the external magnetic field line will be smaller, or you can say it will decrease. That is when we move the magnet closer to the coil. So remember this. So what happens when we move the magnet away from the coil? It is going to be exactly the opposite to what just happened here. Okay, so let's reverse the process here. I forgot to do this over the hours. So you can see that these are basically from north to south, yeah? Okay, so now I'm going to reverse this. So what happens if we, actually I could have kept it here as well. What happens if we move this magnet away from the coil, okay? So in this case, this is what is going to happen. Perhaps I'll have to draw the drawing as well, maybe. Okay, so let's keep this one here. I'll try to draw on the other side here. So this is one, okay? Let's see if we can, I don't think I can do that, but okay. Now, all right, so here's what happens. Like we still have the same coil. Okay, this is the same coil, let's say. This is the galvanometer again, and perhaps I'm kind of like drawing it a bit smaller maybe this time, just so that you'll see what happens next. Or we have enough space as well to just make sure that we have enough space. Here's the magnet, let's say this is north, this is south. Don't forget, that was the direction of the motion first. Now, this is the direction of the motion here. So let's say V is in this direction here. So what happens exactly when we do this? First of all, you can see that there is a magnetic field lines, correct? So we'll say these are the magnetic field lines. Again, going from north to south. These should be concentric, but you get the point here. So even if it is not exactly, these shouldn't overlap though. Let me just fix them before you say, magnetic field lines cannot be crossing or whatever. Okay, so there's the magnetic field lines. These are the direction of the magnetic field lines, always going from north to south. True? Yes. So, but this time, here's the direction of the motion. So what exactly does it happen? Let's say this is the magnetic field lines. So of course, these are crossing this. But here, what happens is this. As you move this, let's say, magnet away from the coil, what will happen? Now, the number of the magnetic field lines that are crossing the coil, will it increase or decrease now because you're moving it away? So clearly, it decreases. If that is the case, then of course this decrease in the magnetic field lines is obviously will induce a current here. Okay, let's draw this one as well. So once again we have a magnetic field line, you can say, yeah? And then when the number of the magnetic field lines, let's say, that are crossing the cross-sectional area of this coil here will change, of course that means we have a change in the magnetic flux, okay? But this time, the magnetic flux is decreasing instead of increasing. So if that is the case, of course, this act will induce a current in the coil here. But the current that is, of course, let's go with blue here. All right? Will induce, don't forget, will induce a current in the coil here, okay? But this current, of course, obviously, first of all, a potential difference, you can say, or electromotive force here, yeah? I could have done electromotive force first, but I'll just do them like parallel to one another. This electromotive force will induce a current because we have a closed circuit here. This current will also produce its own magnetic field, okay? But these two magnetic field lines will always oppose one another, okay? So these two will oppose one another. In another word here, okay, by the way, one thing that I forgot to mention here, you can say the magnetic field lines, when we were bringing the magnet close, it is opposite. You can say in the opposite direction to one another. But this one here, because the direction of the motion is this way, so this side is north, this side, how does it oppose that? If this side is north again, then it would be very easy to repel this one. I would just push it away. But we said, since these two are opposing one another, so how do you stop this magnet from going away? By pulling it or by pushing it further? Of course, by pulling it. But how do you pull this magnet? By having a north of this side or a south? Of course, it has to be a south, yeah? So in this case, of course, we will say this side of the coil has to be south in this case. And then the other side is going to be north here. And the galvanometer, it is going to shift in the other direction. Let's call it negative for now. It doesn't matter, yeah? This is 0, and then this is opposite to what have happened here. But you do know that if this is south and this is north, now there is an attraction between the two. So this coil tries to prevent this magnet moving away. So how does it do that? But you do also know that. So now we can say the magnetic field line for this coil, it is obviously going to move from north to south, yeah? So you can say something like this. It's not perfect, but now it is, if it is moving from north to south, it's going to be like this. And of course, within the coil, it is going to be in this direction as well. So you can see that when the magnet is moving away, you can see that the direction of the magnetic field in both the magnet and the coil will be in the same direction. So if the magnetic field lines are in the same direction, what do you get as a result? Previously we said the direction of the magnetic field are in opposite directions, so as a result you can say the net or the total magnetic field line will decrease. But if the magnetic field lines are in the same direction, yeah, do we subtract them or add them? Normally vectors, we add them if they're in the same direction. As a result, we can say the strength of the magnetic field line or the external magnetic field lines will increase as a result of this. So once again, these two will oppose one another, and of course now the current will be induced, but because these are in opposite direction, the current will be induced in the opposite direction here. So this is what happens when we move the magnet away from the coil. You can see that. So we can summarize this by let's summarize these two both together. When we bring the magnet, or when we push the magnet into the coil, there will be an induced current. This induced current will produce its own magnetic field. These two magnetic field lines will oppose one another, or to put it more precisely, you can say the magnetic field line that is induced here will oppose the change in the magnetic field line of the external field, let's say, or external magnet. But once the magnet is moved away, okay, and by the way, the magnetic field lines are in opposite direction here. But when the magnet is moved away, we can say, once again, there is a change in the magnetic field line. This change in the magnetic field line, you can say, or magnetic flux to be more precise, will induce a current in this coil here. The current in this coil will also produce its own magnetic field. Now these two magnetic field lines, in order to prevent this from moving further away, will oppose it, yeah? So of course, in this case, if this is north, this is going to be south, yeah? But if you look at the direction here, the direction of the magnetic field lines are both in the same direction. As a result, the external magnetic field will increase in here. And of course, the current will be moving in the opposite direction. And this is what happens. Okay, and the reason why this happens is basically to get, you can say, there is the energy conservation, yeah? So we can do that, you can say, to conserve the energy here. So that was basically in detail what happens when the magnet is brought closer to a coil, and then what happens when the magnet is moved away from the coil. So that'll be for the second case. When a bar magnet is moved away from a coil, the magnetic field within the coil decreases, we said. Okay, but remember, that is within the coil. Don't forget, yeah? The reason why, because these magnetic field lines are going to decrease. They are pulled away, let's say. Okay, but there is one thing you have to be careful with this, yeah? The external magnetic field increases. It is true that the magnetic field line within the coil decreases, okay? But the external will increase in this case. So a current is induced in the circuit. That is for the second case, when it is moved away, yeah? Okay, and then the induced current, let's say, in turn produces its own magnetic field here, okay? And then the induced magnetic field opposes, you can say, by the way, it's opposite in direction to the decreasing magnetic field, which means that the magnetic field of this two would be the same, or the direction of the two field will be the same. The external, if that is the case, the external magnetic field will increase. And of course, we can say the coil and the receding magnet, the magnet that is moving away, create a pair of forces that attract one another. And that is all about the property of the current that is induced here. So of course, this one says when a bar magnet is moved away from a coil, the induced magnetic field is similar to the field of the bar magnet within the orientation shown here. Okay, and of course, this is, after that, we can talk about Lenz's law. Yeah, so what is Lenz's law? Basically, we've been talking about the property of the current that is induced. Yeah, and of course, we can say this is also sort of like talks about the direction of the current that is induced. So we can, like Lenz's law in short, if I go through this a bit quick, we'll say it's the magnetic field of the induced current is in a direction opposite to the change that creates it. So let's say if we bring the magnet closer to the coil here, this is north, yeah? The other side of the, or the polarity of the coil here, there will be a magnetic field around it, yeah? The polarity of this, or you can say this side, or the magnetic field for this part, this end of the coil is going to be opposite to the one that is approaching it. So these two will oppose one another. But remember, it's not opposing the magnetic field of this coil. It is opposing the change of the magnetic field of this. In another reason, we can say, if you like, for example, hold this magnet close to a coil, nothing will happen. But it only induces or produces the electromotive force of the current when this magnet is moved closer or further away. So it doesn't affect, or it doesn't, let's say, prevent the magnetic field line here. It affects, or let's say, opposes the change of the magnetic field, because once you're moving this closer or further, there's a change of this, and that is what it opposes. So this is basically what Lenz's law is about. It says the magnetic field of the induced current will be in a direction such that it opposes the change that created. So it is always opposite, you can say, to the change that creates this one here. So that is if north brought north. So how do we oppose north? By making this is north, yeah? But once you move this one away, this is north. And how do you oppose it? How do you prevent it from going further? By making it south to try to pull it so that it doesn't go away, yeah? This is basically all about Lenz's law. But few tips that are very important regarding Lenz's law. All right, let me go through this real quick. It says Lenz's law is used to find the direction of the current only, not the magnitude, because magnitude will later on come. Let's say that'll be using Faraday's law, okay? So this is just for the sake of the direction of the current. The field of the induced current does not oppose the applied field, you see? So the field that is basically induced on the coil will not oppose the field of the magnet or the bar magnet, let's say. It will only oppose the change in the magnetic field of the magnet, just like what I have mentioned here. So the applied field change, the induced field tends to keep the total field strength constant. That is very important because we'll say Lenz's law does not provide information about the magnitude of the current, so just the direction. And the last point is also very, very important. Actually, the last 2 points are very important here. Lenz's law does not provide information about the magnitude of the current, it's just about the direction. And then, based on this, we can say the Lenz's law illustrates the principle of energy conservation, yeah? So once it is approaching, we try to stop it so that we keep the total the same. Once it is moving away, we try to keep it, let's say, prevent it from moving away so that we keep the total the same, and this is how, or why it is called the principle of energy conservation, or Lenz's law can illustrate that, you can say. These Rosati questions, I believe these are easy enough. I expect you to go through them, and hopefully you do them well. Okay, now take a look at this one. It says, explain how Lenz's law allows you to determine the direction of the induced current. We said Lenz's law says that the induced current in a circuit will always flow in a direction such that the magnetic field of this induced current will oppose the change of the magnetic field that created this current, you can say. Okay? Of course, in the, you can say magnetic flux that caused it, that's the same thing in here. Rapidly inserting the north pole of a bar magnet into a coil of wire connected to a galvanometer causes the needle of the galvanometer to deflect right. So if we insert the north pole of a magnet into a coil, it makes the galvanometer needle to shift to the right. Yeah? So that is the first part of the question. Here's what will happen to the needle if you do the following. If you pull the magnet out of the coil. So if the needle shifted to the right, so what happens if you, like when the magnet is inserted? So what happens to the needle if you pull the magnet out? Of course, it's going to shift in the other direction, which is obviously going to be shifting to the left side in this case. What happens if you let the magnet sit at rest in the coil? We said if there's no relative motion between the two, there's no induced electromotive force. And if that is the case, the galvanometer needle will go or point show 0. That means there's no induced electromotive force induced. Then it says thrust the south end of the magnet into the coil. Now, instead of, let's say, inserting the north pole, let's say you insert the south pole. So what happens? Once again, the galvanometer needle will shift in the other direction. First time it was shifted to the right. Now it is going to shift to the left because you reverse the polarity of the magnet. And then it says, explain how Lenz's law illustrates the principle of energy conservation. That is also very, very important. We'll say, by opposing the change in the external magnetic field. So the induced magnetic field obviously prevents the energy of the system, let's say, from increasing or decreasing. So it always tries to prevent let's say the energy, or let's say by opposing the changes in the external magnetic field. So like we said, once you bring the magnet closer, the external field tries to get let's say increased, yeah? So the energy or the current that is created will have a magnetic field that opposes this to keep the total the same, let's say. But now once you're moving, or once the bar magnet moves away, obviously, let's say that or you can say this external magnetic field is now about to decrease. So how do you oppose that? I mean, how do you keep it the same? By opposing this so that the total does not become less. So this is how we can keep the total always the same, and that is, you can say, conservation of energy, you can say. Does dropping a strong magnet down a longer pipe tube induce a current in the tube? If so, what effect will the induced current have on the motion of the magnet? That is also something very important. If I go through this real quick, I'll say, let me draw perhaps somewhere here. Let's see if we have, yes, perhaps I can draw it here. Let's say we have a pipe. This pipe is long, right? So if we drop a magnet, it says a magnet, yes? Or bar magnet into this coil here, that's north and south, let's say. This pipe obviously is it is a conductor. So once you do this one here, let's say this is north, this is south, there's a magnetic field around this one. We can change this one. There's a magnetic field around this one. So once you are dropping this into this, obviously, there's a change in the magnetic field as it, for example, approaches the metal, or you can say this conductor, or as it moves downward. So there is a magnetic field. So there will be a current, you can say, within this pipe. But the current within this pipe will also have let's say, its own magnetic field. Okay, and of course we can say this magnetic field of the pipe will be opposite to the magnetic field. Can I draw? Okay, let's just say there's a magnetic field here. Okay, this magnetic field, that's not even close. All right, so let's say there's, oopsie. All right, so let's go back to this. Let's choose a different color. There will be a magnetic field here. Okay, by the way, this magnetic field could be horizontal, but that is not the case at this point here. We'll just say there will be a magnetic field. Let me just make one giant magnetic field. It would be best, perhaps. Okay, there will be a magnetic field here as well within the coil. Let's just put it that way. I hope you can see that, yes? This obviously, first there will be a current within this pipe. This current will produce its own magnetic field. Now this magnetic field of the pipe will oppose the magnetic field of the bar magnet, and of course this would slow the motion of the bar magnet, so it allows it to fall very, very slowly to the other end, let's say. Okay, but remember, this is only true, or it happens only if this pipe is totally, you can say there is no cut, it's kind of like closed, you can see at the sides here. But if there's a cut in there, remember, you will not have a closed loop, so this will not happen, or this will not take place. It will immediately fall, let's say due to the free fall, gravitational free fall, assuming there's no air resistance. So this what happens, we'll say, will it affect it, or will it induce a current? The answer is yes. The field of the induced current will oppose the magnetic field, let's say, of the magnet opposing the magnetic force. The opposing magnetic force slows the motion of the permanent or the magnet inside the couple rod. If the pipe was not closed, the current will not be induced. And of course, this one here, the last question, says, what happens if you have two magnets, but these two magnets, you can see that, their opposite poles are attached, and if you insert this one to the magnet, you can see that the magnetic field of this magnet, or one magnet, cancels the magnetic field of the other magnet. It's not writing, okay. The magnetic field of one magnet cancels the magnetic field of the other magnet, so it's almost like there's no magnetic field acting on this one, so that induces no magnetic field. Now that is all for this session. Inshallah, next time we'll continue from regarding more like how we can use Lenz's law or find the direction of the current. But till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.